The products of Friedel-Crafts acylation reactions contain a carbonyl group linked to an aromatic ring. At the end of the last video, we noted that if we could develop conditions to reduce a carbonyl group to a methylene or CH2 group, we could use that as part of a broader synthetic strategy to synthesize primary alkyl benzenes in which the carbon connected to the benzene ring is primary. This is difficult or impossible to do using alkylation because of the rearrangements that will occur when we try to subject a primary alkyl chloride to Friedel-Crafts conditions. We're going to focus in on two methods in this video, and both of these convert a carbonyl group, C double bond O, into a methylene group, CH2. This amounts to a reduction because we're replacing bonds between carbon and an electronegative heteroatom, oxygen, with bonds between carbon and hydrogen. And this amounts to the donation of electron density back to the carbon, since there's much less polarization in these CH bonds than there was in the original carbon-oxygen bonds in the starting material. We're giving electron density to the carbon, and that amounts to reduction. Here's a general scheme for the reduction of a benzylic carbonyl group into a methylene group. And don't forget about the implied hydrogens on the benzylic position in the product, as these help us see the bonds made and broken in these reactions. Two complementary methods are used to affect these benzylic reductions, and they involve either acidic or basic conditions. In that sense, they're complementary, as we'll see. The first is the Wolff-Kishner reduction, and this occurs under strongly basic conditions. It involves the use of the reagent hydrazine, N2H4 or H2N NH2, as it's often drawn to suggest its structure, as well as the basic reagent KOH, and multiple equivalents of KOH are required to make this reaction go. In addition, you often see high temperatures used in the Wolff-Kishner reduction. Something like 200 degrees C is not uncommon. In addition to the primary alkyl benzene product, which I'm going to abbreviate AR for aromatic CH2R, the byproducts of this reaction include nitrogen gas, which leaves irreversibly bubbles out of solution, as well as water. Ultimately, the carbonyl oxygen becomes incorporated into a molecule of water. In the Wolff-Kishner reduction, because we're using strongly basic potassium hydroxide, we call the reaction conditions basic. And this is important to note in case the substrate has any functional groups within it that are prone to react with base. These substrates are likely ineffective in Wolff-Kishner reductions since they'll use up the base without affecting reduction of the benzylic carbonyl group. And we'll see an example of that in a second. But for this reason, because of the incompatibility of certain functional groups with base, an alternative method was developed that uses acidic conditions, and that's called the Clemmensen reduction. In the Wolff-Kishner reduction, the true reducing agent really is the base. And in the Clemmensen reduction, we take a different approach where we use as the active reducing agent a metal, specifically zinc, in the form of zinc-mercury amalgam. And the mercury here is really just there to moderate the reactivity of the zinc. The combination of zinc-mercury amalgam with HCl leads to the Clemmensen reduction. And here, the products include, once again, the reduced primary alkyl aromatic compound, ArCH2R, along with zinc chloride, ZnCl2. One interesting point about this byproduct is that this contains zinc in the +2 oxidation state, showing that zinc, which started as zinc metal in the zinc-mercury amalgam, has undergone oxidation, as it must if the organic substrate undergoes reduction, as we showed previously. To highlight the importance of understanding both the Wolff-Kishner reduction and the Clemmensen reduction, I want to look at two substituted aromatic compounds for which these reactions would give very different results. And I'm going to draw them twice on both sides to show their compatibility with the two different reaction types. The first is a para-amino substrate generated from Friedel-Crafts acylation of aniline, and the second is a metasulfonic acid substrate generated either from sulfonation of the aromatic carbonyl compound or Friedel-Crafts acylation of the benzene sulfonic acid. These two substrates would react very differently under Wolff-Kishner and Clemmensen conditions. And the problem here is that each contains either a basic or an acidic functional group. The benzene sulfonic acid substrate contains an acidic hydrogen attached to the sulfonic acid group, while the amino nitrogen contains a lone pair that can potentially act as a base. What happens when we combine a substrate with a basic lone pair, such as the amino group, with strong acids, such as concentrated HCl? Well, that creates a problem. Rather than the HCl participating in benzylic reduction as it needs to give us the desired product, it's just going to protonate this nitrogen. And so the reaction won't work as advertised. Instead, we'll just observe an acid-base process. On the other hand, these conditions are totally fine with the acidic proton in the sulfonic acid group. they won't touch this group because it doesn't react with acid. It's an acid itself. For this reason, the benzene sulfonic acid substrate will work fine under acidic Clemmensen reduction conditions. How then can we get the aminobenzene to react properly? Well, if we subject it to basic conditions, now we're in a situation where the basic lone pair is totally fine existing in the presence of potassium hydroxide. Both are bases, and bases don't really react with each other. For this reason, the reaction works fine when the aminobenzene is subjected to the basic Wolff-Kishner conditions. However, now the benzene sulfonic acid presents a problem, since this hydrogen is acidic, and in the presence of as strong a base as KOH, potassium hydroxide, we should expect an acid-base reaction to occur between KOH and the sulfonic acid group. This means once again that the reaction won't work as advertised. Rather than observing benzylic reduction, we'll observe an acid-base process involving the sulfonic acid and the basic potassium hydroxide. And so we can see that we need either the Wolff-Kishner conditions or the Clemmensen conditions to address both of these substrates. And the key to recognizing that was seeing the potential for acid-base chemistry within these functional groups in the side chains of the benzene ring.